So here I'll do a little bit of a summary of what we did to review for this first part of our Year 8 acceleration. We have a bit of geometry, and from Year 7 we have parallel lines. Okay, so parallel lines are kind of funny because the definition is that they don't ever intersect, okay? But we don't really ever use that, and a lot of the properties of parallel lines that we do use is about corresponding angles being equal, alternate angles, co-interior angles being supplementary, alternate angles being equal, corresponding angles being equal. And we're saying these properties are all equivalent. If you note that, a supplementary or two right angles or 180 degrees is what a straight line has as its angle. And we're also trying to relate a little bit. So we're basically taking these three things as equivalent definitions of parallel lines, and we want to eventually relate it to this other definition that says parallel lines don't intersect, but we don't really need to right now. So one of the earliest things we could prove that was kind of interesting with parallel lines is that the angle sum of a triangle is 180 degrees. Okay, so we have angle sum of a triangle. It's 180 degrees, and with that, we already can show that two parallel lines cannot intersect. Sorry, two lines with the property that corresponding angles are equal cannot intersect. So this definition of parallel implies the original definition of parallel, because if they do intersect, they form a triangle, okay? And because this corresponding angles are equal and co-interior angles are supplementary, the base angles of that triangle is already going to be 180 degrees, so that the angle at the point of intersection cannot exist for the angle sum of the triangle to be 180 degrees. So we talked about that, and then we really talked about triangles in some detail. So we talked about acute angle triangles, obtuse angle triangles, right angle triangles, and those are really classified triangles because they have to add up to 180 degrees. And we showed how everything could really be broken up into triangles. Triangles can be broken up into right angle triangles, and therefore basically polygons can be broken up into right angle triangles. So in a sense, a lot of geometry can be broken up into triangles, and we don't really need to break it up much further than right angle triangles, because basically we can know everything there is to know about right angle triangles. Okay, so we talked about similar triangles, essentially being scaled up versions of each other, and the criteria for similar triangles was basically which pieces of the similarity picture do you need to actually know the whole picture. So if you knew all the angles were equal, equiangular, that was enough. Okay, if you knew all the if you knew the sides were all in the same ratio, that would be enough. And and so on. And similarly, congruency. So that's saying when triangles are actually the same. So it's not just in the same ratio, but the ratio is actually 1. And the types of criteria for congruency is very similar. So there's probably 1 for each corresponding one for similarity. You have congruent triangles. It's like angle, side. It's 2 sides and the included angle, right angle, hypotenuse, side. And the similarity, it's kind of similar to this, except with ratios of sides instead of actual equality. And two angles being equal is the same as three angles being equal. Having one side in the same ratio doesn't really say anything. So for similarity, it will be just AAA. SSS will be three sides in the same ratio. SAS will be two sides in the same ratio, and the included angle is equal. And the right angle hypotenuse side is kind of interesting because it's not really that obvious that for a right angled triangle that the hypotenuse and the side determine the length of the other side. So this is really, so SAS really is, you really need angle to be included in between the sides, and it doesn't work if it's not in between. But this is kind of saying it does work if the angle happens to be 9 degrees and it's not in between. Okay, and then we prove Pythagoras' theorem. And one of the consequences of Pythagoras' theorem might be that you do know, given two of the sides of a right angle triangle, you know the third. Okay, but you could also do it independently of the theorem because you don't actually need to know the lengths of the sides, you just need to know that they're determined by the other two sides. Okay, and so we really went into a lot of depth with triangles, and once we talk about congruence and sides, we talked about isosceles triangles, properties of scalene triangles. We didn't have any properties of scalene triangles, isosceles triangles, equilateral triangles, and then we use this to talk about quadrilaterals. We didn't care too much about quadrilaterals, but we are interested in how to reason with them given triangles, because we kind of claimed knowing triangles was not to know everything, so we wanted to see that in action for quadrilaterals. For example, we looked at parallelogram and looked at the definition of a parallelogram, I guess, would be the opposite sides are parallel, but then there's some other properties such as like the diagonals bisect each other, the opposite sides are equal in length, and we explored how they could be deduced as consequences and whether or not they could actually be defining properties in that they could deduce back, rederive the original definition of parallelogram. We talked about kites, rhombuses, rectangles, squares. Kites, trapezium, sort of, rhombus, square. Not as like a list to memorize, but just as a way to exercise our minds. Okay, and we explored them all very rigorously. We tried to prove them if we could. And then we kind of went, angle sums and exterior angle sums are also gotten by doing triangles. So we maybe took a bit of a leap. We went past pentagons and hexagons and went straight to circles. Talked a little bit about the area of the circle, the circumference of the circle, from the point of view of maybe similarity, something like that. We had a way to measure pi by sort of measuring the volume of a cylinder using water and that kind of thing. Okay, so we really went from, a line, parallel lines, sort of throughout like an entire, the list of the kind of shapes that you could get. That was our treatment of geometry. Okay, and when we learn the other topic, hopefully we can actually relate it back to this topic to make things all very nice. And once again, we're learning this not to remember the facts of these things, which you'll probably remember easily if you remember the other things, but as a way to develop our minds. Okay, as a way of thinking precisely about something, and this is the right stimulus material to help us do that.